Hello everyone. This is a video about the shell model and magic numbers which comes under the paper Nuclear and Theoretical Physics, which is for BSc Physics 5th semester students of University of Mysore. As we know, in the last video, that is when we were discussing about the liquid drop model, the liquid drop model explains the stability of the nucleus, the phenomenon of radioactivity, the formation and decay of the compound nucleus, and the phenomenon of nuclear fission. And the liquid drop model also helps us to calculate the atomic masses and binding energies of the nuclei quite accurately. But it fails to explain the high stability of the nuclei with magic numbers. Also, it doesn't explain the measured spins and magnetic moments of certain nuclei. So here the objectives of this shell model is to understand the behavior and the stability of the nucleus, to study the nuclear energy levels by considering the Pauli's exclusion principle, to account for the existence of magic numbers and certain other nuclear properties in terms of nucleon behavior in a common force field, and to account for the ground state spins and magnetic moments of the nuclei, and also to understand the nuclear isomerism. The learning outcome after this video is the student must be able to understand the behavior of nuclei with magic number. It draws circumstances that lead to think of shell structure of the nucleus, explains the presence of magic numbers lead to the development of the shell model of the nucleus. This shell model, which was formulated by Geoffrey Mayer in 1948, and he uses Schrödinger wave equation or quantum mechanics to describe the energetics of the nucleons in a nucleus. And the scientist assumes that each nucleon moves independently in the nucleus, uninfluenced by the motion of the other nucleons. Nucleons form closed subshells within the nucleus in a manner like that of the electrons do in the case of atoms. Hence, it is named as shell model. The shell model, which explains that each nucleon is assumed to possess a spin angular momentum, as we know, and it is equal to square root of s into s plus 1 into h cross, and along with the spin angular momentum, it also exhibits an orbital angular momentum which is equal to square root of L into L plus 1 into h cross, where these S and L couple to form a total angular momentum of about square root of J into J plus 1 into h cross. This theory, which assumes that LS coupling holds for the lighter nuclei and the JJ coupling holds for the majority of the nuclei. And this spin orbit interaction splits each state of given J into 2J plus 1 substates. And in the shell model, it explains that each shell which are filled when they are having the number of neutrons and or the number of protons in a nucleus, if it is about equal to two numbers 8, 20, 28, 50, 82 or 126 neutrons or protons, and then these numbers, which are nothing but called as the magic numbers. Nuclei of such magic numbers of number of neutrons or the number of protons are found to have zero quadrupole moments. Hence, they are spherical in nature. The odd proton or neutron which could not be paired that contributes to the spin. The nuclear magnetic moments are explained in terms of J values of the odd nucleon in the nucleus, and hence the total magnetic moment by considering the orbital magnetic moment as well as the spin magnetic moment, which will be equal to mu is equal to mu L plus mu S. Then what are the experimental evidence in favor of these magic numbers? Now we know that helium 4 will be having the proton and the neutron number as equal, that is equal to 2. as well as in oxygen, and that is also having the number of protons and number of neutrons as equal to 8, which are called as highly stable in nature. Now, this a graph between, if you plot a graph between binding energy per nucleon and mass number, shows a sudden increase in binding energy per nucleons for calcium, strontium, Sn, lead, Pb, etc. Nuclei having number of nucleon as magic number are in abundance as compared to other nuclei. For example, if we are considering oxygen 16, calcium 40, strontium, lead, etc. These are nothing but called as stable in nature. Nuclide with its Z as magic number have the highest number of isotopes is nothing but the calcium 40, which will be having the highest number of isotopes, that is it has 6 isotopes in it. And nuclide with its neutron number as magic number has the highest number of isotones. There are 5 naturally occurring isotones with n is equal to 50, and the stable product of the natural radioactive series is lead, which has Z is equal to 82 and n is equal to 126. And these both are the magic numbers. The energy of the emitted beta particle is very high for magic number nuclei. The electric quadrupole moment of nuclei with magic number is 0. The first excitation energy of the magic number nuclei is very high. And this is the pictorial representation for the shell model for the atoms which are having the magic numbers. Nuclei having Z are n is equal to a minus z equal to one of the numbers, that is 2, 8, 20, 28, 50, 82, 126 and 184, which are highly stable in nature. The ground state of the nucleus is represented as 1s of square for n is equal to 1, L is equal to 0 and J is equal to L plus S, which is equal to half. Hence the first shell contains 2 nuclei, which is a magic number. The second shell has 2 subshells, that is 1p4 and 1p2. For 1p3 by 2, n is equal to 1, L is equal to 1 and J is equal to L plus or minus half, contain 4 nucleons, and 1p 1p contains 2 nucleons, and the total nucleon number in second subshell is 8. Similarly explained for the other shell also. And what are the limitations of this shell model? It does not predict the correct values of L in case of certain nuclei. The 4 stable nuclei, that is 1 hydrogen, lithium, boron, nitrogen, do not fit the scheme of this model. Could not explain the observed large quadrupole moment of odd A nuclei, particularly those which have their nucleon number far away from the magic numbers. And these are the references for the shell model, that is Arthur Beiser, which is the Concept of Modern Physics 6th edition, TMH New Delhi 2008, and